Hello. Hello, good evening, everyone.
Good evening, sir.
Okay, so let's today is the live coding session. So last week it was not done. So we will cover today week 6 and week 7, both problems. Okay, so Avilas has raised the hand. Yeah, Avilas.
Sorry, sir. Just a quick question, sir. Where can I download my answer scripts? Quiz one.
Answer script you did not receive on your course page or on your dashboard.
Sir, in the dashboard, all I see is the quiz one question papers and feedback forms. I was confused where to download it.
No, feedback form is different, but you got the PDFs now, so that where you can see answers and questions all.
Sir, that's the question paper and different question paper formats that I got. Like the answer transcripts we get, right? So, what we did the exam, like what options did we take? That sheet.
Okay, so that answer script, I'm not sure. Any other student you have received? Yeah, from other students, have you received the answer script?
Sir, usually what happens is we get to download it from my dashboard. We go to documents for download there. We get answers transcript. I checked there 2025 quiz to term 2. There was no transcripts for the subjects as well. So,
Okay, so maybe it is not uploaded yet. So maybe team will upload it later. So because I'm not sure, you can check with support regarding this. So I don't have any idea. So someone sent some link. You can see this. Avilas, okay, you can check these links.
sure, sir. I will check it.
The sport checker. Okay. Okay. Any other query? Anyone before starting? Okay.
Yes, sir. This link is working. Yeah, I got it. Thank you.
Okay. Okay. Fine. Okay. Let me share my screen. So we have released 2 weeks problem now, 3 from week 6 and 3 from week 7 today. So as you can see on the portal, live coding, these problems are available. So we will try to. What happened, Kiran?
Um, two week session, 2 week
So
coding.
last week actually we have done for the revision, na? So that on Friday. So we have not covered this. So week
Oh,
6. So because of that, this is pending. So I'm not saying that you need to do today all the problems. You
um,
so next live coding session we can also cover. Okay.
I have an AQ pending. So today is the deadline. So I'm wondering you till
Oh,
what time it will extend.
okay.
Sometimes it extend to 11 and sometimes.
Hmm. Okay. Otherwise, after week 9, we have one free week, so we can cover the things later. If any like this practice problems are pending, not the graded one. Graded one have the fixed deadline you have to complete. Okay, so this is the first problem I have opened. So you can see, I think the text is very small. Question statement. Hmm. So this is the problem. I hope you have seen the content of week 6. That is where we covered the heap. Okay, max heap, min heap, and binary tree, and these topics we have covered. So this is the problem based on that. Write a function type of heaps that accept a heap A and return string max if input heap is max heap, and min if input heap is min heap, and none otherwise. Okay, so that means we are getting one list, okay, as a heap. So you know that we can implement our heap as a simple array or a list, like, okay, because the elements are arranged in the level wise in the tree. So we can represent our heap in the form of list or array. So now you need to check this heap makes max heap or min heap, or this is just a an heap, okay, that not follow any property. So how we can write the code for this? This is the question here. So you can see we are taking one list and we are just calling the function type of heap A, and we need to return the answer max, min, or none. Okay, so how we can check this? The question is now how you can check the heap is a max heap or min heap, or else none. So let me just solve this on paper and pen. Like suppose if we take this example, so how we can draw this heap? Like as if one will become a root node, and then two will come on the left child, three will come on the right child. Like this, we can draw this as a heap. So now four, and then five, and then six. Okay. So now I had just make as a heap tree. Okay, in the form of binary tree. Now you can identify that this is a max heap or min heap. How you will check?
This is a min heap. No?
So how you figure out this? What is the definition of min heap or max heap?
The roots will be smaller than the
Uh,
children.
Root is
Uh,
the
Only
smallest
root.
of
root is
the.
smaller than their children. It's a mean hip, and root is bigger than their child root. Then max.
So why you are saying root? Only root. So,
Parent.
so any node. So if we talk about any node, so like this is a root node. For min heap, this should be smaller than to or equal to their parents. Sorry, children's.
Each node is
Okay.
smaller than its children.
So any nodes, this property should be fulfilled by every node. So like 2, this is also a one like parent node we can consider for 4 and 5. So 4 and 5 are the children for this. If we compare this property, if we just compare these elements, so this node is also smaller than to their children node. So this property should be fulfilled in each pair of these parents and children. Okay. For max heap, if our parent node is greater than or equal to their children, so then that if this property fulfilled by every node, then that heap is a max heap. So this means we cannot figure out only by just looking the root node. Okay, so for this we cannot figure out this. This is a min heap. We have to check every possibility. So only this 2, 3 have the children. So we need to check at least for 1, 2, or 3. Leaf node we not required. This is not required to check because they don't have the children. So in our code also we need to follow this logic. Without checking each combination, you cannot figure out. Okay, so you have to check each. Then in this array representation, how we can figure out the who is the parent of any children? By indexing you can figure out. You know how we can calculate the left child or right child with the help of index or parents.
Parent is a time minus 1 by 2.
So just compare 0. 0 is the index for this. 1, 2, 3, 4, 5. This is the indexing. So for any node you can find out, so what is the total length of this heap is total, how many elements we have? Total 6 elements we have. Okay, 0 to 5 index. So for any node we can figure out who is the left child or who is the right child. So we can check like left of I. Okay, left of I means left child of I. So suppose if I am checking for 1, so this index is 0. So what we can do, 2 into what will work here?
2i plus 1.
2 into I plus 1. Okay. For Ri, we can just consider 2 into I plus 2. So this formula you can apply for each part. So suppose if you want to check who is the left, who is the left for this 3 node. Okay, so index is 2. So 2 into 2 plus 1. So you are getting 5. So you can see 5 index is the left for this. And who is the right for this? So if we are calculating the Revati, can turn off the mic. Some noise is coming. Okay, so who is the right child for this 3? So if we are calculating 2 into 3 plus 2, and then we are getting 2 into 2. 2 into 2 plus 2. So we are getting 6. But we have the length only from 0 to 5. This is the size of our heap. So if we are getting any index which is greater than to the last index, so that means that is not exist. Okay. So during the calculation, also note this: if you are getting any index which is not exist, so that we cannot consider as a right child. So in this way, we can figure out left child or right child for any parents. Now, this is the first thing how we can figure out. Yes, Neha.
So I didn't get the logic behind how we are getting this formula. Can you explain again, please?
Huh.
Like 2
So
into
indexing,
I.
we are representing. Okay. So we are representing this list or array as a heap. Okay. So here indexing, how we can represent logically this as a heap. So let me open my notepad. Okay, let me here. So 1, 1, comma 2, comma 3, comma 4, comma 5, comma 6. This is given inside the list, but logically this is a heap because we are just considering that we are getting one heap. So how the equivalent heap for this is, so first node will become as a root, then left and right. So this order will maintain actually. We will fill all the labels and left to right order. So 1 is now coming at the root. Now 2 will come at the left child. 3 will come at the right child of this. Then again left 4, and then 5, and then 6. Okay, so these are the value. Now, and this is a complete actually binary tree. We are not skipping any child during this order. Okay. So here, if we just mention the index, so index is just like a 0, 1, 2, 3, 4, 5. Same index order we can mention in the tree. 0, 1, 2, 3, 4, 5. I'm just making this as a logically to understand, and we will just perform this operation on the directly this list representation of the heap. Okay, so how we can identify this? Suppose if we have this heap in this form, list form. So how we can identify that who is the right child, who is the left child of any element? Okay, any node. Suppose if I just ask that who is the right child or who is the left child of this element, this element. Okay, and you don't have this type of representation, graphical representation. So how you will figure out this? Who is the left child of this three? Who is the right child of this three? So we can calculate by these formula. So as I mentioned that left of I, we can directly calculate 2 into I plus 1. So you will reach at the left child. You can validate this in this tree representation. So you can check for every any I. So suppose if I is equal to 1, okay, and we are checking that who is the left child of this and who is the right child of this with the help of this I value. Okay, so this I equal to 1 for this. So now 2 into 1 plus 1, you are getting 3. 2 into 1 plus 2, that is equal to 4. So you can see 3 we are getting left, 4 we are getting right. So this formula is calculating left child index and right child index correctly.
Okay, sir. Okay.
Okay. So
Sir,
Yes.
we, huh.
we can just take the leaf nodes towards the right side of the from the middle, and then we can just compute their parents and just
Hmm.
add them to the front,
Yes.
right? So that will
So
reduce the time complexity.
yeah, correct. So during checking, this is a min heap or max heap. We will not start from the last node. We will directly jump from the node which has at least one child. Okay, because this leaf node not have any child, so no need to check with this. Okay, we will only check from that node which have at least one child. Okay, so we will start from 3, then 2, then 1, and we will check this property. If parent is smaller than or equal to their child's, so this condition is true. Okay, so we have to check this condition for min heap for every node. So 3, 2, 1. Same condition we have to check for max heap. Okay, so for 3, for 2, for 1. If both are actually not satisfied, that means this tree, this tree is this input is not either min or max. So that means answer should be none. So how we can do, how we can reach to this index directly? So we will figure out that the formula for that also. Okay, so we have, you can see we have total 6 vertex here, and in this example, how we can come up to the direct parent node where we should start actually. So we can use the formula
and,
length. Hmm,
and back to
yeah.
minus 1.
Sorry, length.
Length of
Length of
this
this
parent
heap. Okay. So 6. Suppose in this
double slash
example, we
2
have the 6 and minus 2 you are
by
saying.
2 by 2 minus 1
Okay, by 2. Okay,
minus
6
by
divided by 2 minus 1. You are saying this?
yes.
Huh. So we are getting 3 minus 1, 2 index. Yeah, correct. And just check for 5 also. So this is working fine or not. So 5, because 5 should also start with the 2. Okay. So that minus 1. So we will get 2 and then minus 1. You can see for this example, this will not work. Okay, you are saying length. Okay, okay, okay. 1 second. So for suppose if we have right example, then we have total vertex 7. Okay, so 7 floor 2 minus 1. Then you are getting 3 minus 1 2. Yeah, this will work. Okay, this is correct. So in this way we can figure out that which node we should start that have the actually childs. So we have validate this formula. So length divided by 2, float division. Okay, float division by 2 and then minus 1. You can apply this. And this value, by this value, so float this length divided by 2 minus 1 to 0 index you have to run. Okay, for each value you have to check.
So this formula is for what?
We are just
Floor
checking
division.
that our this we are checking that from which node we can start the checking process, because
Okay.
each pair we are just checking that this pair is a min heap or max heap or like nothing. Okay, then we will check this thing here, then we will check this here. For each combination of 3 nodes, parent, a left child and right child, we will check this property, this is a max heap or min heap. So from where
Okay.
we actually have to start.
Sir,
Okay,
from Li and Ri, we are checking the right node and the left node. Is that
li is the left, ri is the right. Okay, l means left of I. Okay, if we have the index I, what is the left child index we are calculating by this li. If we have I
okay?
index, what is the right child index, so ri.
Okay, got it. Thank you,
Okay,
sir.
so in this way we will start the process. Now how we can solve this? Okay, so let's see the code. So let me increase the size. Reduce this. Okay, so let's write this function. So I'm just typing diff and this type. Okay, type of heap, and we are just receiving this a from this. So how we can do? We can just make a two different function. Okay, to just easy to understand. Just we will make this as a two different function to check this is a max heap or this is a mean heap. Okay, so I am just writing the things. So first condition if, and I'm just writing the one another function to check min heap. So I'll just give the name here. So min like is min heap. Okay, is min heap, and here we will pass the a. Okay, if this value is equal to true, then we will return our answer min, and this is a string actually. So we will write like this min. Okay, same way we will just call the another function. So if is max heap, okay, max heap, that we check for the max heap. So I'm just checking that equal to and true, and then we will return.
Hello, sir.
Hmm.
Sir,
Yes,
when is OPP exam?
when is
OPP exam?
in August month, next month.
Before
Okay,
quiz?
no, after quiz 2. Quiz 2 is on 3rd, no, 3rd August. So
Yes, sir.
after quiz 2, after week 9, so syllabus is week 1 to 9 actually. Okay, so maybe after week 10, your exam will be happening. Dates are given on the documents. So why you did not actually read the document, grading document? Every details are given. Okay, so if both conditions are not true, then we will return none. And this is also a string. So this is our just a basic main function, which we need to write. But out of this, we will define our each function. So is min heap. So is min heap, and this is receiving a. Inside this, we will validate this. Okay. So now we will perform the range. So we will start from the zero index always. Okay. So zero index we will use to start, and because that is the root node, and from that we will just move to that length and floor division by 2 minus 1. Okay, so that till that index to check with every pair. So now for I in range, we will start this range from 0 and to len of a and floor division. So floor division uh, okay 2, and what should be the value here? So minus 1 or any idea what we are going?
We
So
can
we
leave
have
the -1 because we have to go till that last thing.
because by default the last value will not be considered. Okay, so if we have the size like 6 for this example, so 6 floor division 3, and 3 will not be considered, so this loop will this for loop will run from 0 1 2. Okay, if we have the 7, still this loop will run from 0 to 3, so this is fine. Okay, so let's I'm checking, just validating this for other example. Suppose if we have this example, so 0 1 2, then 2 floor division by 1, and then 0. Yes, it will work fine. Okay, so this is the range we will check. Okay, and now what we will check? So we will check the condition where our this min condition is actually breaked. So we are checking the if our this tree is min heap or not. So for this, for each index we will check this property. So for this property, if so now we will compare our parent to left child, or we will compare our parent to right child. Okay, so both we will compare. Then if any property is not fulfilled, so parent should be less than or equal to our left child or right child. So we need to check this property. So a of I, so a of I is representing the parent. If this is greater than this is okay, we are checking the okay. So by this, okay, we will check any condition when our this condition is actually break. So if ai is greater than of a, what should we write in here? Okay, so left child, so 2 into
2i minus 1.
2i plus.
Plus 1.
So if our ai is greater than to left child, so that means this is not a min heap. We can break our process and we can directly return the answer if this condition is true. Or okay, so and another condition for right child, when you're calculating the right child, so it we will also check that if this right child index is not out of the range. Okay, so for our condition, if ai is greater than this right child, okay, so a of 2 into I and plus 2, so this is the right child. But there is a chance that if you are calculating the right child, but that doesn't have that index is not exist, so in that case this if a statement will give the index out of range, this type of error. So we will also make one more and here. Okay, so we will also validate this. Our ai should be length. Okay, actually length. So this 2 into I, 2 into I plus 2 plus 2. This should be less than 2 len of A. Okay, so this condition. So I hope you understand this, why we are checking this condition.
Sir, please repeat that condition after and.
Mhm. So we are checking this condition because we have seen one case. So like for this example, one, one, two, three, 4, 5, 6. Okay, so we are checking this condition ai with every index. So like this 0, 1 and 2, we will check for all these three. So when we are checking with 0, it's fine because 1 and 2 both are left and right, both childs are available. If we are checking with 1, so this 3, 4, 5. So for one index, left and right childs are available. And when we are checking this 2, so there is a possibility that right child is not exist. But if we will suppose if we will apply this condition, so this will work on left part work fine. But if we will check like this second condition, so a of I, okay, so I is here 2, this is greater than to a of 2I, so 2 multiply 2 plus 2, so that will become 6. Okay, so this condition will be actually checked. So in that case, this 6 index is not exist. So because of that, this will give the error. This expression will give the error index out of range. So because of that, with this condition, we are also validating that when we are calculating any right child index, we will always check that that index is lesser than to the length of our list. So what is the length of here? We have 6. Okay, so this 2 into 2 plus 2, this is the right child calculation. This should be always be less than 6. Then this means this index calculated right child index is exist. If this is greater than, then this is not exist. Okay, so because of that, we are checking this condition. But if we are using AND operation, so this condition should be come first before this. Otherwise, what will happen? Because if you have any two condition with the AND operator like C1 and C2, so I hope you know this logic. So always what happen? First condition is executed for. Okay, first C1 will be executed. If C1 return false, then second condition will not be executed. Actually, it will be ignored. This second condition will not be checked, not be executed. But if this first condition is true, then only second condition will be executed. Okay, this will be checked. So in this
Got
case,
it.
okay, in this case, if we will put this index validation condition first, then our execution will not be happen for this part. Okay, so we will not get the error. If we will put this expression first, then again we will get the same problem. Before checking the validation of index, we will get the error out of index. So I've written this incorrect. So let me just make it correct. Okay. So this part actually should be written before this condition. Okay. Now, so like this, if any condition is become true, so means our tree is not min heap, and we can directly return our answer. Return false. directly. False. Okay. Now we,
So,
yes.
sir, then for the uh, when for the second case itself, it will return.
No,
Uh,
no.
if the
Hmm.
it
So
will check for the
just just think about this example for this. So how this code will work. Okay, so one, then two, then three, then four, then five, then six. Okay, so this code will start from zero index, zero, one, two, three, four, five. So what is the range for this is zero, then one, then two. Only this range, this loop will run. Correct. So for first value I, zero. So you will check this condition zero. Huh, okay, okay. You are saying we need also one true statement.
I think, sir, these two conditions will
Huh,
be
huh,
in the brackets. No?
So it will be outside for loop, no?
huh. That condition should be written outside. Yeah, because if this is not true, then we should also return here.
Sir, I think it works if you like put some brackets or with these two second two conditions if you put in a bracket. I think.
No, that will work fine. This will work. It will not give any error. Okay.
So just to avoid confusion, we can use brackets.
Huh.
That's what
Yeah,
he's
you can.
trying to say, I think.
Okay, just put.
Or
Otherwise, code will not give any error. But yeah, you can just understand these two conditions are like this. Okay. Sorry. Correct. Fine. So this is for parent with left child. Okay. And this is for parent with right child. We are validating. If any condition become true, we will return false because this is the condition we have written if a parent is greater than to the left child or greater than to the right child. So that is not the case for min heap. Okay, so we will directly return false without checking anything. So that means function will stop at this point. If our loop is completed and this condition is not satisfied anytime, so at the final we will return true. So that means all the nodes are satisfying the min heap condition and we finally return true. So now this is the part for min heap. Now similarly we can write for max heap. We will only change the condition for the parent and child. So same things. Now we will change the name of function max. Okay, is max heap. Now range is fine. Now this condition. So we will just write less than, and here also we will write less than. Okay, then return false, and all will remain same. So now this become a solution for this. I hope this is clear. Max heap, we are just checking the reverse condition. If any time our parent is become less, so that is actually a like false condition for the max heap. Let's see if it is giving the correct answer. So these publics are pass and privates are also pass. Okay, so now these function, if both are not satisfied, so finally this will return none from the main function. Any doubt in this? Any query?
no, sir.
No, sir. Thank you.
Okay.
Sir, in line 4,
Huh?
the or after condition.
This condition.
Yes, sir. That condition or condition.
So this part is clear. This is simple part, same part. We
Yes,
are
sir.
checking the parent with right child. Okay.
Yes, sir. This part is
But
clear.
there is a situation that if right child is not exist, but we will actually blindly calculate it like this for left and right for each node. Left will always be possible. Okay, but right for right child index, there is a chance that that is not exist. Okay, I have seen this example now. So the same example, let me write again. So 1, 2, 3, 4, 5. So in this case, suppose here one more less than elements are there. Okay, so how many elements we have? 5. Okay, so 5 floor division by 2 and minus 1. So you will get 2 minus 1 1. You can see you are directly reaching this node. So this is the index 0 1 2 3 4. Okay, so you are directly reaching this node. If you add one left here, then you will only reach this second index. So now total node becomes 6. 6 floor division by 2 minus 1. So that is now 3 minus 1 2. So you can see now you are reaching at this index. So if left child is exist, so this is the always case where from you are starting the checking, left child will always be there for that node. But right child possibility is there. So for last node, you can see we are just reaching to this node to check, but this does not exist the right child. In that case, our code can give the error like index out of range in the code if you will calculate, because in our logic we are not checking that like our child is exist or not. So if you will not write this condition, so by default this will check. So I you can see this part will execute actually. Okay, so a of I, so for this index a of 2, and this is greater than a of 2 into 2 plus 2, so you will get this index 6. Okay, so in code you will get this index, but this a6 index is not exist in this. Okay, only last index is 5, so you will get a error. So we are just preventing this error, so we don't want this error to stop the code. Because of that, before this validation we are checking that if our calculation is this index calculation is less than to the length of the list, so then only we will check this condition. Okay, if our right child is exist, then only we will check compare parent and right child. So this is happening here. Okay, if this condition is false, this will not be checked. So our index out of range error will not come. Okay.
Okay, sir.
Okay, so this is the solution for first problem. Let's move to the second. Okay, so this is just a long solution you can apply here. So this is find redundant edge. But logic wise you can understand easily. So write a function find redundant edge e comma n that accept an edge list e in increasing order. Yes, Sandeep.
So can you collapse the left pane? The
Hmm.
font is too this thing.
Okay.
And little bit if you can increase the font of coding.
Hmm.
Right.
It's fine. Hmm. Okay. So write a function find redundant edge e comma n that accept an edge list e in increasing order of the edge weight, where all edge weights are distinct and the numbers of vertices n labeled from 0 to n minus 1. In a connected undirected graph, and the function return a list of redundant edge in increasing order of weights. So by removing this edge, the graph should remain connected with the minimum total cost of edges, minimum cost spanning tree. Okay, so I hope you remember. So what we are doing actually, we have one list that contains all edge information. Okay, now we want to remove the edge one by one.
So we want the edges that form cycles.
Huh.
So that is what it is asking.
Huh. So finally, what we will got? We will get the spanning tree, minimum spanning tree. So this is, I think, which algorithm we can apply here?
Kruskal's algorithm. If the find of u is equal to find of v, then that edge is added. That edge
Ha, so
is
that.
revealed.
So we can apply simply Kruskal algorithm here. So that will only contain the edge. So that will provide the total cost minimum. Okay, minimum cost spanning tree. So this is the purpose here. So here you can see the sample input. So in this example, we have 4 edge. Okay, and out of this edge, if this will make some graph. Okay, this will make some graph. So how we can do, how many vertex we have? We have 4 vertex. So 0 1, like 0 1 2 3. Okay, in this way. So what we can do, you can simply start the process with the smaller edge. Okay, and which we can sort this. We can sort the edge with the so in the respect of weights. So 10 20 30 40 50. So this is
It's
already
added in
sorted.
the sorted form.
This is already sorted. It is given increasing order. So we will just pick one edge and we'll mark into our graph. So 0 to 1. So that means this is not creating any cycle. So this will consider. And then 1 to 2. So 1 to 2 with 20. So this is 10, 1 to 2, 20. So this is also not creating any cycle. So 20. And 2 to 3. 2 to 3 is also not creating any cycle. So this is uh, 30. And after that, 3 to 0, this will create a cycle. This is creating a cycle. So this will not be considered. And 1 3 5, this 50, this will also create a 1 3, that will also create a cycle. So that will also not consider. So these two edge will not be considered. So that means these edge we are removing actually. We are not considering in our graph. So these s we should in our answer. Okay, so here we are not getting the cost of minimum spanning tree. We are just figuring out that which edge will not be considered in the this spanning tree. So that list we actually figuring out. Okay, so some modification in Kruskal algorithm. When you are just applying the Kruskal algorithm, you are considering that which edge will consider. But here we will just note down that which edge will not consider. So you can implement this algorithm with the help of like union find structure, union find data structure. So in this question, I think that suffix code is not given, but okay. So you know about the that Kruskal algorithm, Prim's algorithm, you can apply in this, but you have to remember the implementation at least one of the algorithm, either Prim's algorithm or Kruskal algorithm, and then you can figure out this. Okay, so that implementation I think is big implementation. So let me see. That will take too much time. So because of the Kruskal algorithm. So this is the one algorithm you can see here. We are collecting the tree edge. So this is the tree edge. If we will ignore these tree edge, then we will get the total non-tree edge actually. So that is our task here. Okay, and the same things we can do with the help of union find data structure. So that is the another like week 6 we have seen union find data structure. So this implementation we can do this improved Kruskal algorithm. Here you have this algorithm, and we can use this implementation to solve this, and that will also give the same. So I'm not writing this completely. Let me just take this uh, this part here. So I'll use this. So this is covered in week 6. Okay, don't worry about this type of lengthy code. Questions will not come in the OPP exam. Okay, so this is given here because you can take this code. So now we have this make union find this code. So I hope you know the purpose of this code. What is the purpose? So first things, make union find. This is the complete code. Inside this, we have this find one function. Okay, that actually return the component value. What is the component means? Leader. We can consider anything. So if we have connected components, so like if you have uh, this connected component like 1 and 2, this is one connected component, then 3, then 4, then 5, okay, and then 6, and then 7. Okay, so like this three connected components are there. So during the process we always just when we actually start with always the single node, so like 1, like 1, okay, 2, 3, and 4, 5, 6, 7. Suppose this is all are actually distinct and not connected, and then we start connected these things. Okay, initially we mentioned that the component of each node is number itself. Okay, so the component for 1 is 1, and 2 is 2, 3 is 3, 4 is 4, 5 is 5, 6 is 6, 7 is 7. So this is just representing a each are distinct connected component. Now when we start connecting them with the help of edge, so suppose we are getting 0 to 1 or 1 to 2 edge. Okay, so when we connect this, because this is not creating any cycle, so we also update the component value for them, and we make the same component for this. Okay, so when we are connecting this 1 and 2 by one edge, so this will represent a one component, so that component value for this should be represented by a one value. So either we will update both component value by 1 or maybe both by 2. In this way we will update. So when we are connecting like this, suppose I am updating by 2. So now you can see the component value for 1 is 2 and component value for 2 is also 2. So this will help to identify the cycle. Okay, so this find process actually return the component value, this value. Suppose if we are checking that what is the component value for 1, this is 2. What is the component value for 2, this is also 2. And union process is actually just added the edge into the graph, and in this process we check what is the component when we are adding. Okay, suppose if we are adding like 3 and 5, suppose we are getting as 3 and 5, this is the edge, and we want to check that this edge will be considered or not. Okay, so this is creating cycle or not. So what we will do, we will check the component for 3 and we will check the component for 5 both. So currently what is the component for 3 is 3, what is the component for 5 is 5. If both component value are distinct, okay, not same, then we can add that edge into our spanning tree, new spanning tree. If components are same, then we cannot add, that will create a cycle. So this is the logic. So here 3 and 5 will add because the components are different, but after adding this, both value will become same. So like suppose this will update by 5. Okay, now suppose new edge come 1 and 3. Okay, so this will add or not. So for 1 component value is 2. Okay, for 3 component value is 5. So both are different, we can add this will not create a cycle. So we can add this, but after adding this all will become same. So 5, this will also update by 5, and this will also update by 5. So we need to update this. And now question comes is, when suppose we are adding 2 comma 5, this edge. So here you will get the component value 2 is 5 and the component value 5 is 5. Now both are same. So that means both are already connected, because of that component value is same. So if we will consider this edge will create a cycle. So we will not consider this. So with the help of this make union find data structure, we will just check for this for every edge. If edge is creating a cycle, we will not add. That will come into the answer. Okay, so this is the union find data structure. So you can see C old, C new. We are just checking the UV and this things, and after that we are checking if cell this find make union find. Okay, union UV always check C new size. Where we are checking the condition union self size union. Okay. Okay, okay. So that condition we will check in the another code. So this is just a union operation. So that will directly add the edge. So this is the process. If our that components are different, so we will update our component into the remaining part, which will connect actually. Okay, so this is the union. But we will check before this. We will check the process. We will check the component value. If that are different, that only we will call the union function. Okay, let's see how we can use this code in our that minimum spanning tree process. So let's so here now just define the function. So diff and find union. So that function which we require to write here. So that e comma n. Okay. So in this function now we will just check. We will call hmm, okay. We will call a object of this spanning tree. Okay, so st equal to, and we are just creating an object of this make find. Okay, because we will just use this methods for this class. So make union find this, and we have created object. Now we will use the method for this. And first this is the set of vertices. Okay, so initially we are just setting, this is the initialization for the given graph. We'll just make union find. So this is the initialization. This will create all the vertex separate and will assign the component, also will assign the like members that value and size also, that will also maintain the size. But we can only use this component that will help our. Okay, so what we are doing, we are just calling the function set st dot and make this method. So this will create a totally distinct component for it. After that, for each edge, now we have one sorted. Okay, we have one sorted edge list that we are getting in the E. Okay, and our output is the redundant edge. So we just create one list, redundant edge list. I'm just giving this name empty list.
Sir,
Hmm.
sir, in the make union find, don't we have to give the parameter e, the list of
No, no, no.
edges?
This is just an object of this class. Okay, here in it you can see we are not, there is no parameters
Sir,
required.
in make union find method, there is a parameter
Oh,
vertices, the
okay.
list
For
of.
this, okay, this you are saying. Okay, yeah, correct. Here we need to pass E.
So, but I think
Not
e is
N,
for
not N,
setup
N,
also.
N, N.
Yeah, okay.
Okay. So this is just for the output list. We will return this list. Those as will not be considered into this, and we will add into this. So now we will start the process for each edge. So for each edge in E. Okay. So this is our edge list E, and that is already sorted in increasing order. So no need to sort anything here. Now for this, for each edge, we will do the process. So if st dot find. Okay, so we will use the find to check the component value for the vertex for each edge. Okay, find, not this. I think this is the find. Okay, so name is find. Yeah, okay. So find, and inside the find we will pass the vertex. So as we are getting these things, you can see we are getting tuple. So the index tuple, first index is representing source. Okay, second index is representing the destination, and third index is representing the weight on that. So we will just read the first index here. Okay, so that each edge. Okay, each is also incorrect. Each edge and index 0. So this, for we are checking the component value for this. If this value is not equal to like find again st dot find, and here same each, and now second index 1. Okay, so we are just checking source vertex and destination vertex which are connecting by this edge. So for these, if components value is not equal, then we will union this. Okay, we will add this edge into our graph. Okay, so this is just like a st dot union So union, and here we will pass this edge. So edge, each edge and 0, okay, comma each edge 1. Okay, so this is the requirement for union. You can see we need to pass u and v, which vertex which are connecting to this edge. So here we pass this.
Sir,
Hmm.
this vertices is a iterable, but here you are passing n. N is an integer. Maybe I think you can write a range of n.
Where you are saying?
Can you scroll up a bit?
Function definition, sir.
Yeah, here
Find redundant edges.
yeah, here vertices is an iterable, no? In make union find of self comma vertices.
No, we are passing this value, no? U and
No,
v.
no, no,
No, sir.
not that.
Line number 6.
Oh, you are saying here, like self.
Yeah, here vertices is an iterable, but you are passing n. N is the number of vertices.
No,
So this we have defined
vertices
here,
is
no?
just a
0 to.
number. I think he's getting confused.
No, vertices value is just a number. Okay, so
Yes.
number four vertices are there. By default, this indexing is 0
Yeah,
to 3.
okay, so okay.
Okay, this is the integer value. And here you can see we have just called the union. So this will combine, this will add this edge into our spanning tree. Okay, so this will consider, this edge will consider actually. Okay, else part, if this condition is not true, so that part, this means we will consider that edge into our redundant edge. So we will add that edge here, red list dot append, and simply that each edge. Okay, and this list we will return from the answer. So return and this RED. So this is the idea of this code. So we are only interesting which those edges are will not be considered in our spanning tree. Okay, those will be removed. So that will come here. So with the help of this make a union and find. So this is union find data structure which we have implemented, and we are just using the method of these find union and make union find initially. So then we will simply check. Okay. So let's see. Yeah, it's working. Yeah. So I hope this part is clear. What is the each method work here? So make union find, how this find union and make union these are doing. Here we are not using this size and member these things information. Okay, so anywhere. Okay, so here we are updating, but this you can also remove because here this is not required. Okay, so this is the additional work we have done during the implementation of this. So with the help of component value, we can do this. Okay, so I hope this is clear how we are just checking this edge is creating a cycle or not.
Yes, sir.
Okay, then let's move to the third. Okay, so this is the write a function find kth largest. So this problem is related to the like by okay binary tree find kth largest that accept root. Okay, BST is given. So binary search tree is given. Now we need to figure out that find kth largest in our binary tree, binary search tree, not binary tree, binary search tree. That accept root as a reference of root node of BST of n elements and an integer k where k is greater than 0 and less than equal to n. The function should return the kth largest element without doing any modification in binary search tree. The complexity of the solution should be in order of log n plus k. Okay, so here you have binary search tree, not any array or like this binary search tree. So let's just make this binary search tree. Here as input one sequence is given, but one binary search tree you are getting in your function. Okay, you are getting the root of the binary search tree. So first thing, just understand that what we are actually trying to get here. So just take this input which is given as input for binary search tree, and now consider the how the binary search tree will look like for this. So 5 is the first inserted node. Okay, I am creating the binary search tree. I hope you know the process of binary search tree creation. This is also very important for quiz 2. Okay, any sequence is given, we always start from the root node, this insertion process, and we check where the new element should come. Okay, and so we will compare always from the root node. So 5 is the initial empty node, so we will add directly. Now 4 always we will start from the root node. When we will get the empty location, we will add. So 4 is smaller than
Sir,
to
are
the.
you sharing anything?
My pen is not visible on my screen.
Your
Visible.
Visible, sir.
screen is not.
Visible.
No, on the
Visible, sir.
same question page, I am just writing. Okay, so when I'm just pushing this, when I'm just inserting this 4 into this binary search tree, we will start from the comparison from the root node. So 4 is smaller than to the root. Okay, so we will move to the left side. You should know that if we have the element smaller than to the any node, we will move to the that should come onto the left side in the according to the binary search tree rule. So 4 is smaller than 5, so that should come onto the left part. And there's no node connected to compare again. So we will directly add this here, 4. Okay. Now next 6. 6 we will start from the 5 root node, and now 6 is greater than to the 5, but there is no another node connected to the right. Okay. So 6 will add here. Now 3. 3 is smaller than to the 5. Okay. We will always start from the root node. Don't miss this step. So 3 is smaller than 5. Then we will move to the left. Left again node is available. So we will compare to the that node. 3 is smaller than to the 4. So that means this should be come onto the left. Now left is empty. So we will add here. Now 2. 2 is smaller than 5. Then we will move to the left. Then we will compare to the 4. 2 is smaller than 4. Move to the left. Then we'll compare with 3. Then this is again smaller than 3. So this should come into the left where the empty place. Okay, not 2. Now 1. Okay, so 1 again from start from 5. So this is smaller than 5. Move to 4. Smaller than 4. Move to 3. Smaller than 3. Move to 2. Smaller than 2. Then it will add here. 7. 7 is greater than 5, and move to right. Greater than 6, move to right, and right is empty. Set here. So now this is the resultant binary search tree for this input. Okay. Now in this input, you need to find the third largest element. So third largest means this is the first largest, this is the second largest, this is the third largest. So answer should become 5. Okay, so this we need, and you are getting this binary search tree in as a parameter into the function root node, this address, and you have to identify the kth largest element from this. One way you can do, if you know about the traversing operation. Okay, traversal operation of a tree, binary search tree or any tree. Okay, so there are some traversal method we have, like in order traversal, pre-order traversal, post-order traversal. So in order traversal, if you apply in order traversal into the any tree, any binary search tree, you will always get a sorted order, increasing order. Okay, so suppose in order traversal you apply on any binary search tree. So this is just a simple straightforward binary search tree. Suppose if I am just getting a random binary search tree like 10, like 10, okay, and this 3, then 5, then 1, then 15, and then 13 and 14. Okay, and like 20. Okay, this is also a binary search tree. So here elements are arranged in this way. If I apply the in order traversal on this binary search tree, you will get a sorted order. Okay, so 1, 3, 5, 10, 13, 14, 15, and 20. In order traversal always provide a sorted order. So this is the one way to solve this problem. So you can apply the in-order traversal, but that will traverse all the nodes. And after that, you what you can do for kth largest element, you can just return the element from this side. Okay, kth element. So k is 3. So third element from this side, you can directly return. Okay, so this is the one way. I hope you know about the in-order traversal, how the in-order traversal actually applied. This is mentioned in Week-7, Week-6 also. Recursive code we generally use for this in-order traversal, and that is only 3 steps function, recursive function. Okay, so I'm just giving the hint for this. So in order function we have, suppose, uh, in order function, and that is apply, suppose, ptr any node. So inside this function we write like if our ptr is not equal to none, then first step is move to left node. Okay, so just recursive call in order on the ptr left child. Second step is just print current node. Ptr dot info or anything. Okay, current value of the node. And last third step is recursive call again. So in order ptr on right child. So only in the recursive call, only these 3 steps are required. Your traversal will happen by this recursive. So if I just write like this, L, P, and R steps, okay, in 3 steps: left recursive call, print statement, right recursive call, and that applied on the root node. So L, P, R. Okay. So first step in the recursive solution, you know that if this is the first step is recursive call, so your execution control will be moved from to the new call. So here left call is the first step. Your control will be moved to the left child directly, and this the same function will be applied on the left child again. Okay, and same step LPR. Okay, now the first step of this is also left recursive call. Then you will move to the left child if I exist. Then LPR. Okay, 3 steps again. So left is not exist here. So because of that, this step will become empty. This is the base case. Okay, if ptr is not equal to null, then we are performing this. Then first step is will not affect anything and will not execute p. Second step is print statement for this. Okay, so print step, what is the value here? 1. So that will print first. Okay, now right recursive call. Again, right child is not there, so this step will also be not executed. So now all 3 steps are completed. You will revert back to the previous step where you are coming from. Okay, so now left part is done. The second step is print, so 3 will print. Okay, now right recursive call, you will move to this side. So LPR, 3 steps again. Okay, so left recursive call, no left child, print statement, so 5 will print. Okay, right, no right child. So all these 3 steps complete. So previous you will return the previous, all 3 complete. Okay, so now all 3 complete, you will revert back to the previous call. Okay, so now left, this execution happened. Now print statement, so 10 will print, you can see. Okay, now right recursive call, so right is LPR. Again, this is the first step, left recursive call, left is there, so left call, so LPR. Okay, so now left is not there and print, so 13 is printing. Now right recursive call, so LPR, no left, print, 14 is print, R. Okay, now this completed, return back. So all are completed, now return back. So this L is done, P, so 15 will print, and right recursive call, so left, and then no left, then 20 will print. Okay, so you can see you are getting increasing order by this in order traversal. Now same is pre-order and post-order. So pre-order is just if you change this print statement before this in order left. Okay, so that you can write PLR. This is pre-order traversal and apply the same process in this way. And post-order traversal is just move this print statement after both recursive calls. So LRP. This is the recursive order we will change. Then our algorithm will become different. So for in if you apply the in order traversal, you will get this sorted order, and you can directly return the answer for this. But for this question, it is asking the solution some efficient solution. Okay, so you can see this is asking something log n plus k. So n is here total number of elements in the tree, and log n plus k steps if we can figure out this. So how we can figure out this? So if you know, if you have any binary search tree, so there is a how you can figure out the max element and how you can figure out that min element.
Rightmost is the max and leftmost is the min.
Yes, correct. Okay, so if you have any binary search tree, it's like this 10, 3, 5, like 6, 2, 1, 15, 30, 20, like this. Okay, suppose this is a binary search tree. So if you want to find out the maximum element or minimum element, so this is a simple way. Maximum element will always be come at the rightmost child. Okay, and the smallest element will always come at the leftmost child. So you can simply traverse and figure out this. And so here our task is find to kth largest. So what we can do, if we are just only interested in kth largest, so we can apply a recursive traversal on the right side. Okay, so in this way we will reach at the last element, that will be the first largest. Okay, so suppose here we are moving to the last node and we will reach at the first largest. And after that, when we will revert back, then we can use a counter. Okay, when we can apply we can use a counter when we are reverting back from this. And at that time we will just use a counter. So this is a first, and suppose if our k value is equal to 3, so our recursive steps should be come in this way. So when we will revert back, we will check our all the sorted order elements. Okay, we can think about some in order traversal from this position. Okay, so that means from this what is the second largest, so that our control should be moved to this. Okay, so this is the second largest, so this when we will move on to this side, so we will increment our counter 2. Okay, then we will move our previous third largest, so we will move our counter to third, and always we will also check if our k value is matched with our counter, we will stop the process and we will return the answer. So this is just like if our binary says that tree is balanced. So log n time is for just moving to the rightmost child, and after that just traversing kth position element. So that plus k. Okay. So in this way we are thinking. So we can just write a solution of the recursive solution for this. We have to think recursively here. Okay, so we have to traverse to the last point, and after that we can apply some in order type of traversing from that position. Okay, and we will just use the counter and we will just stop the process when we will reach our kth counter. Okay, so how we can write the code for this? So our task is here to write if find kth. Okay, so here we need, because this function is we need to write, but we want to execute something recursively, so we will use another function to write a recursive. Okay, so or we can write the same also, but we have to return the value to the main function, so that will create a problem. So let's write this function first. So like the diff and find, and this is kth and largest. Okay, largest. Okay, and this function is taking the root value and key value. From in this function, actually, in this function we will call another function, so that we will write a recursive function and we will use some specific variable into that.
Sir,
So hmm,
don't we need this class tree?
what class?
Don't we need this tree?
We require
Tree
this
class?
tree. So root is the reference of root node. Okay, so from root node we can traverse actually in any side.
Yeah.
So
So is it given in the backend code?
so it is given in our function. So here you can see in the question statement,
Hmm.
root that accept root as a reference of the root node of BST.
Okay.
Okay, we have only this input. We need to traverse our tree in this way so we can figure out the kth largest. Otherwise, if simply list is there, we can directly figure out, just apply the sort and then figure out. Okay, but here this is a binary search tree. So now we will call our another function from this. So like kth largest, I'm just giving the name kth largest, and I'm passing the root node only in this. Okay, and this is the function, and here we will return something result. So that actually we have to use some global value here, because we will use the recursive call, and we will restate the rightmost child, and then we will traverse back, and in that process we will get our kth largest element, and then we will store that result somewhere, and we will return that result. So we will use some global variable here. So one global variable I am taking count, and that I'm setting 0. Okay, initially count is 0, and finally one is result, and that is I'm just setting -1. Okay, you can set with any value which is not possible. So I'm setting here -1, and this result value should be updated with the final kth largest value. Okay, so we will return this value, global value, in our function. So res. Now in the function definition, we will define diff and kth largest, and we are getting only root here. Okay, so in this function now we will use this count. Okay, and we will use this count, global count and result in this function. So we will define this global count comma result, res only. Okay, now we will check if root dot. So root dot right, actually if you see the definition in this right side, what we have the value. Okay, so we have the class tree. Okay, in this class tree, so we have self dot value as a this value of the node, self dot left as a left child reference, self dot right as a right child reference. So root is also a one object of this class. Okay, that will contain the value of this left and child, right side, and value. We can directly access all these value. So root dot right. Okay, if this value right, this does not equal to none. Okay, so that means if we have root dot right child, if right child is exist, then we will move to the rightmost child. Okay, so this is just a uh, iterative function to move to the rightmost child. So in this process, if this is not equal to none, we will simply apply our this. Okay, here largest. So that means we need to apply. Okay, so here we will just call the this function find kth and this, and we will pass here root dot right.
Sir, we can just take a while, no? While the root dot right not equal to none will
You can use
set
while
root is
also.
equal to root
Yeah,
dot
you can use
right.
while also. Okay, and for loop, while loop, you can use any type of loop. So this is just a recursive type of things, because if root dot right does not equal to none, we are calling the same function, this function, on the root dot right. Okay, and we are passing the same value. So again, the new function will start from the same thing. So kth largest on root dot right. So that will check the same things again on the right. If again right is exist, that will move again. So this is the one way. So recursive way we will reach to the rightmost child. But after this process, so this is the one part we have done. So now after that, this recursive call will come back. Okay, once we will reached at the rightmost child. So at that time, this if statement, this part, second step we will consider as a, so one this call is finished. Second condition we will take as a count plus equal to 1. So that means after reaching at the last node, now there is no right child. So this second step will execute. Okay. So second step will actually just increment the count, because we have reached at the first largest, and now we should increment our count. So initially this count was 0. So after reaching at the last node, this count will become 1. That will represent the first largest value. Okay. And now we will apply our condition. So if our k, this count value is equal to k, so at that time we will
The colon will not be there.
where, oh yeah, correct,
And the
okay,
semicolon in the 13th line.
where I mentioned semicolon,
13th line.
13th line. Oh, okay, good. Actually I'm also doing the C programming now, so that because of this happened. Okay, so count is equal to k, and then here actually once this value is matched, so that means we have reached at the kth largest element. At that time you can store this result into your global variable result. So root, this root value dot value. Okay, so just store this value result, and from here apply the return, only return. So this will actually stop the process. Okay, and so this is our part, and so this is the one part where we are moving to the right. But another thing is, so we are, you can see we are applying a in order type of traversal. So if right is not exist, we have to check left also. So we will apply the same algorithms, find kth largest on root dot right, left. So this is just a reverse of in order. So root dot left comma k. Okay. So if you see in the in order traversal, what we have done, we have applied the left recursive call first, then print statement, and then right recursive call. Because and then we are getting the increasing order. Okay, here what we are doing, we are applying the right recursive call, then in between some processing, and then left recursive call. So in this way we will get a decreasing order. Okay, if you apply this in order traversal and you change the order, just take first step R, then P, then L, you will get a reverse order, in decreasing order of the element. So same type of process we are doing. We have written some first right recursive call, so that will reach at the right first largest, and in between at the place of print statement we are doing this part. Okay, so this is just a right step, this call is a right step, this part is just a like is a print step, and this is a left recursive call. Okay, so right p a, so this is just like a in order traversal but in the reverse order. Okay, so in this way you will reach at the last element, after that you will traverse like as a in order traversal in the decreasing order way. So in between you are also checking that if you have reached at the kth position or not with the help of count. At that time you will return empty, and you will stop the process from this function, for this function. Okay, so let's make a graph and see how this will work actually. So let's I'm just creating a small graph and see how this will work. So like this 10, okay, and here this is given 5 and 8 and 3 and 2, this side 20 and 15 and 35 and 30 and like 45, okay. And suppose we are looking for the fourth largest, okay, k value equal to 4. So this is the k value 4. So just apply the dry run of this function. So we are applying this is a root initially. So we are applying this function on the root node. After that, we have set count equal to 0, res equal to just a any value, random value, or which is we will store for the result. And now we will check if root, okay, if root dot right is not equal to none, okay, then only we will do this. So in this case, we will just look the find this, okay. So the same operation we will apply on the right child here, okay. Again we will apply the same things. We will check if right is not none, so we will move to right. Then again we will apply the same things, and then we will move to right. Now in this case you can see right root dot right equal to none. So this means this is not valid for this. So what was the last call? So at this step we have called this step, okay, from 45. So this step will return directly nothing, none, okay. So this is because we don't have any else condition for this function. So when we are calling this and our right dot this root dot right is not equal to none, so else part is not there, so this will not execute actually this part. So we will move to the this step when we are actually on this recursive call from 45. So our count will increment by 1. So that means one count is happened here. So okay, 45. Then we are checking if count equal to k. No. Okay, so this is not executed. Now we will check for the same on the left parts, but there is no left of this 45. So nothing is there. So this will also not execute. Now this recursive call is done. We will revert back to the previous recursive call. Okay. So now this part is done. This part is done. We will increment our counter. Okay. We will increment our counter. So counter will become 2 at this. And now if count equal to k, no. Then again this. Then we will move to the left side. So this our cursor will move this side. Now we will call the same function on this. So there is no left, there is no right first, okay. So then we will increment our counter, so counter will become 3 here. Still count is not equal to k, okay. Then we will check the left side, but left side is also not there. Then we will revert back. So this call is completed. Now we will move back, okay. So at 20, this right part is done. Now counter will increment, so this will become 4. At that time you can see count is equal to k, okay. So now we will store our result equal to root dot value. So at that time this 20 is the value, so that will store in our result 20. And after that we are returning directly, okay, from this. So this is our return statement directly from this condition. So remaining part will not be executed, and the remaining call we will reverse back to the root node. So this is just like a login process, and return we are just moving back login. So two login you can consider, but in between at the back side we are just coming kth position. At that time we are stopping the process. So here you will see, you will get your result in log n height, okay, and then kth traversal, log n plus k steps you will get, okay. So this is a similar example of in order traversal. So you can just check the in order traversal implementation. If you will understand the in order traversal, pre order traversal, post order, you can implement this code also, okay. But then after getting the idea, okay. So let's run this. So this is working fine. Okay. So any part in this? Yeah, Sandeep.
Sir, return will happen correctly, but
Huh.
all the recursive calls we made from the root, they will go back to the root also.
So that will go back to the root. All the call will happen, but then we will not perform any left side. Okay, so this will only return to the root. Then it will not
And
move to the
just
left side.
okay, so just to empty the stack, all the calls will go back to root also.
Yes, because after that we are not updating our counter, so that the count we are not updating our counter. Then it will this operation will left side operation will not be performed.
Okay. But then uh, find kth largest doesn't have a return statement.
That
So
have the return statement. So this we have to return the result. We are storing the result into the this one. So here we are returning this result. So
okay, sir.
from this function, we are calling this kth largest, and this
Uh,
function will call itself, and then that function, that function we call this function. But finally, when we will get this return result value, so that will actually return the result to the main function.
correct, sir.
Hmm?
Now I understood the logic of finding our kth the largest. But what I'm not
Mhm.
understanding is empty returns of the stack of this whole recursion,
So empty
right?
returns from this function kth largest is so if you are returning here, so that is coming to this point.
Uh,
Okay, after that next step is return res. So that is global value. So what value is stored in the global value? So that will return here.
and kth largest is coming here only once, and that is
Hmm.
after
So
final.
once this return is execute, once this return is execute, your overall step will stop actually.
Stop.
Okay.
Right, right.
Yeah. Okay. So this is the third problem. Let's move to the B7 live coding problem one. And B7 problems are based on some man coding process uh, because that greedy algorithms are there. So write a function decode root.ciphertext that accept a variable root which contains the reference of root node. Again, here also you have the root. Okay, because Huffman tree we have, and with the help of Huffman tree, you need to figure out that what is the like ciphertext. Ciphertext is given in the form of a strings using 0 and 1. The function returns the decoded message. Okay, so what is the decoded message for that? So what is the meaning of, you can see this is the Huffman tree. Okay, you know that Huffman tree, each left edge is considered as a 0 and right edge considered as a 1 bit, and each leaf node contains the actual message character. Okay, so this is a Huffman tree. Okay, so all these are actually leaf that contain the actual message. And now I hope you know that how we get the Huffman codes. So suppose what is the code for B? So code for B is just traverse from root to that leaf node. Okay, and what edge weights are coming in this path? So 0, 0, and 0. If you are coming to this, what edge weights are coming? Okay, 0, 0, 0. For C, the codes are 0, 0. So this is the path actually. Okay, so 0, 0, 1. These are the Huffman codes. Okay, for F is just 0, 1. Okay, so for D, this is 1, 0. And for E, this is 1, 1, 0. And for A, this is 1, 1, 1. Okay, so these are Huffman codes. So your ciphertext is made with the help of this Huffman codes, and that is giving into the input. So you can see this is given in the input. Now you need to figure out that what this input is making the message actually. What is the decoded message for this input? So this is just a binary form, and you need to figure out what is the actual message from this. With the help of you have this Huffman tree. So how you can do this? Okay. So this is our problem. So you are getting root. So now you can see you are getting this encoded message in the form of Hopman codes. Okay, when we are combining this, but we need to figure out what is this actual message. Okay, so how you can do this? So for the logic part, what you can do, you can just traverse this string. So this string contains only 0 and 1. Okay, after just take each character, each digit one by one and traverse this Hopman tree. Okay, so in the traversing process, always start from the root node. Okay, so first digit is 0. Okay, so move to this left child. Okay, 0 is because left. Okay, and 1 is right. Then next digit is 0, 0, and next is 0. So in this traversal, when you will reach at the leaf node, okay, so always check you have reached at the leaf node or not. So once you will reach at the leaf node, so just read the message value. What is the value given at that node? So that is just B. Note down this and reset your pointer to the root node again. Okay, so reset your pointer again to the root node. Now next bit is 1 and just move to this side, and next bit is 1, move to this right side, 1, then move to right side. So just when you will get 1, move right, when you will get 0, move left from that position. So again you have reached at the leaf, then just note down this message A and reset your pointer to the leaf root node. Okay, so 1 1 1, this part is done. Now again 0 0 0, same thing will happen, you will reach at the B, and then again 1 1 1, you will get a. Now again 0 0 0, you will get B, but then 0 0, start from 0 0 1. Okay, so then you will come at this side, you will get C. So this is the process you need to apply here. So start around the root and just traverse this sequence tree. When you will reach at the leaf, just note down the character and reset your uh, reference to the root again. In this way, you will get complete message. So this is our task here. Okay, so how I hope you understand that how we are getting the message from the tree with the help of this bits string. Okay, so let's see the code for this. What function we need to write? Pointer question string. Yeah, decode. Okay, so yeah. Sorry. Decode. So here, and we are getting this root. Okay, root, and what we are getting ciphertext. Ciphertext. So these two things we are getting, and variable root and contains the reference of ciphertext in the form of string. Okay, so ciphertext is a string and that contains the digit only. Okay, so 0101. This function we are writing here, and how we can do, we can simply perform, we just get the decoded message. Okay, so dec I'm just taking as a empty string. Okay, we will store our result here, and now we will run a loop. So we will take some variable, temporary variable temp equal to root. This is just a temporary variable, we will use this temp, and every time we will just point it to the root, reset to the root. Okay, now we will run a for loop. So for I in ciphertext, so we are just reading each character of the ciphertext. Okay, character we will read as a digit. So ciphertext, or you can just take like a C character. Okay, or just take D. D is now digit. So now we will repeat our process. So if D equal to what, 0, what we will do, we will pass our temp equal to temp dot left. You can see this class node is given here in the question statement. So left child is represent dot left and right is dot right, and symbol we will read from the leaf dot symbol, and frequency we can also take like dot frequency. So all these things are there. So temp equal to temp dot left. Okay, 0 means left. Now same condition, if this d is equal to 1. But one more things we have to here think here, because d we are getting as a string. So either you can make this as a integer, or you can just write that like this. Okay. Temp equal to temp dot right. Okay. Now this is the movement. After that, we will also check we have reached at the leaf node or not. So this condition we have to check. So if temp dot left, okay, this is equal to none, and if temp dot right is equal to none, so this is the condition, means we have reached at the leaf node. Okay. So now what we will do, we will reset our first thing, we will just note our character, okay, symbol. So tick plus equal to, and that is just a concatenation of strings. So what is our message? So that is actually temp dot symbol. Okay, symbol. So if our node is leaf node, so we will just add that character symbol into our decoded message. And from this position, we will also set our temp to root, this setting. So this is our one loop we will use, and this will do our work actually. Okay. And finally, we will return our result as a DEC. So this is simple iterative code for this. You can see how we are doing. So if d equal to I 0, then we are moving to left. If d equal to 1, we are moving to right. And then we are checking if our current temp node is leaf node. If this is a leaf node, we will just read the symbol and we will append that symbol into our result decoded string. And then we will reset our temp to root again. Okay, so for next character, this we will start from the root again. And finally, we will just do this process for each digit of ciphertext. Okay. In this way, we will get our decoded message. So if you run this, okay, so you are getting the same message as required. Okay.
Sir, what is dot symbol?
Dot symbol is given in the statement that contains the character actually. So you can see dot symbol as self dot symbol equal to symbol. So this is just contains the value b. So leaf node contains the actual character of the Huffman code. Okay, b, c, f, d, e, a. Frequency contain this value actually 2, 3, 5, 5, 10. This contains by the frequency.
Okay,
So I
sir.
hope you know about the Huffman code and Huffman algorithm. Have you seen in the Week-7 or not?
Yes, sir. Sir.
Yes, sir.
Yeah. If you know, if you have already watched the lecture of Huffman coding or this, so I hope you should know. Leaf node contain the actual character, and initially we have the frequency for each characters. So in input part, okay, that is not given. So I hope you know the process how we create the Huffman tree. Let me just quickly explain that also, because that is also important for the quiz too. So suppose for the Huffman coding, you will always get a like characters or frequency. Like you are getting suppose uh, A, B, C, D, E. You suppose you have this 5 character and frequencies are given. So like 10, 5, 40, 3, like 50. Okay, suppose these frequency are given. Now we are asking to generate the Huffman code and Huffman algorithms, Huffman code and Huffman tree for this. Okay, so what are the Huffman code? So generally Huffman codes or Huffman algorithm is used to compress the data, so that actually generate the code for each character, and that also generate the code for which are repeating more times, that will generate the small length code for this. Okay, so in this way, if you will calculate the average number of bits, that will be less. So what happened in the compression techniques and networking? So we use this algorithm. Suppose if we are just taking the same length bit code for each character, suppose if we are taking the 4-bit code for each, so what will be the total number of bits required for this message? Okay, so we can calculate like 4 for each. And how many characters we have total? So we have 10 plus 40, 50, 100 and 108. Okay, so total character frequency, and just multiply this by 4. So that means 432 bits are required to represent this message if we are using a fixed length of the code for each. But if we use the Huffman coding, so this will generate a code where the which code is represent that contains the higher frequency, so length will be less. So how we will get that Huffman code? So that is the process. So this is a greedy algorithm we apply, and we create the Huffman tree in bottom up manner. So we always takes two smallest weight or two smallest frequency first, and we start the that Huffman tree creation process. So let 5 and 3 are the two smallest one. Okay, so we will just create like B and D. So this is 5 and this is 3, and we will just build up a tree. So that's 5 and 3 is 8. Okay, so now this is done. Now combined also, just always consider the addition part to creating the Huffman tree when you have already done. So remaining part 10, 40, 50 and 8. Okay, which two are smaller? Okay, so 10, 40, 50 and 8. So 10 or 8 are the smaller. So just take these two and create the tree. Okay, so this is A and frequency is 10. Now add 8 and 10, 18. Okay, so this is also done. Now 40, 50 and 18. Which two are smaller? So 40 is smaller. So 40 and 18 will be select. So 40, this is C. Okay, and 40, and this will be add. So 58. Okay, now 58 and 50, two are remaining. So that again, like 50. So 108. So this is a Huffman tree process, how we generate the Huffman tree. After that, left is 0, 0, 0, 0. All left are 0 or right are 1. Okay. Now we can generate the Huffman codes. So what is the code for A, B, C, D, E? So A code is just traverse from root to that node. Okay. So A is just like a 0, 0, 1. Okay, and B is so this was E. B is 0, 0, 0, 0. Okay, so 0, 0, 0, 0, and C is this one. Okay, 0, 1, and D is 0, 0, 0, 1, and E is 1. So we are getting this Huffman codes. Now there is a property that here these codes are prefix code. Means you can see no code will come as a prefix to the other code. So if you see this one, this will not come as a prefix of any another code. Prefix means initial. Okay, so 1 is not coming at the prefix. Similarly, this complete code 0, 1 is not coming as a prefix of any another code. So this property by default comes with this tree representation. So what is the length for each? 3, this is 4, this is 2, this is 4, this is 1. Now you calculate the total number of bits for each. So just multiply this. Okay, 10 multiply. So A length is 3. Okay, so 3. For B is just multiply by 4. C is 2. Okay, and D is 4. And 1, this is 1. Okay, just add this. So this is 30 plus 20 plus 80 plus 12 plus 50. If you add this, you will get a 160, 180, and 192. Only 192 bits are required. Okay. So previous method we required 432 bits, but now we are using the compression method with the help of Huffman coding. So our bits are compressed to 192. Okay. And we can identify these bits. If our message we are getting like this, if we are getting this message, if we have Huffman codes, we can figure out, we can decode the message. Okay, with the help of this. So we use this method to get Huffman code and Huffman tree. Okay, so this is the way. So same code we have written to identify the message from the this encoded message. Okay, so I hope this is clear. This code is clear. Okay.
Yes, sir.
Okay. Max selection item. So this is also a one greedy problem. Write a method. Okay, one second. Just increment the font. So write a method max value selection, and that is taking item comma c that accept a dictionary items which where each key of the dictionary represent the item name and the corresponding value is a tuple number of units value of all units, and function accept one more variable c which represent the maximum capacity of units you can select from all items to get maximum value. So this is just like a knapsack problem. Okay, so this is a fractional knapsack actually. This is very standard problem, and this is called as a fractional knapsack. So here you have some items and some units value, total units are given. So like first item, let's explain this problem. So first item you have total 10 unit and the total value for 10 unit is 60. Okay. Second item you have total 20 unit, the total value for 20 unit is 100. And third item you have total 30 unit and total value for 30 unit is 120. Now second parameter is capacity. Now you have the capacity to take only maximum 50 unit. So how you will select the items to take the units to get maximum value? So this is the problem. So suppose if you select 30 all, you will get a 120. Okay, and now you select this 20 all, you will get a 100. So now your capacity is full. 30 plus 20 is equal to 50. You cannot take the another. So this is total cost is 220. This is the optimal solution or not? So this is not the optimal solution. So there is a different way to select the units, and also you can take the partial. Because of that, this is called fractional knapsack. So you can take like 20 from this, 20 this, and 10 this. Okay. So if you take 20 this, then 20 of this, then 10 of this, then what will be the cost? So you can select in different ways. So what approach you will apply here? Okay, so what process we can think here? So we will get the maximum value. So what we can do, we can just take first thing, we cannot directly select based on this value because this is a total cost of all units of the each item. Okay, so 10 unit, this is the cost. So we cannot take like we cannot apply greedy algorithm here in this value. So like we cannot select like this 120 because this is the largest. We will select first. Then this is the second largest. We will select this. Then we will get the third largest. But we can do this greedy approach if we will calculate the per unit value. Okay, so what is the per unit value is here 6. Okay, what is the per value is here 5, and what is the per value here 4. Okay, now we can select the item based on this per unit value. first we will select all the maximum possible item which have the maximum value per unit. Okay, so now we are applying the greedy approach. We are looking the item which have the largest value first.
So how we are getting the per unit value?
Just 60 divided by 10,
Okay,
100 divided by 20,
okay,
120
sir.
divided by 10. Okay, so this was the total cost of all units. So we just divided for the per unit. So 6. Now this is the per unit maximum. So we will just sort the items in the decreasing order, and we will start from the maximum value first. Now, how many maximum elements we can take from this value? So because that have only 10 unit, which is less than the capacity. Okay, so we can take all. So we can take this all. So we will get 60 total value. Now we have remaining capacity 40 after selecting this. So we will just check for the second largest value item. Okay, this 5. So again, this is 20. So we can select all. Okay, because this is less than our capacity. So we will select all. So 20 into 5, again, this 100. Now we have remaining 20 capacity. So from this item, we have only 20 capacity remaining. So we can take only 20. So 20 into 4, that is 80. So that will become 240. So this is the optimal solution for this. Now this process you need to write in this as a code. So I hope this code
So
is,
we just have the capacity of 220, right?
no,
We
capacity is 50. Capacity was 50.
120 plus 100.
No, this capacity is representing the total number of units. So we will just count the unit. Not this value is value, total value, and this is per unit value. So unit value we can consider. Okay, capacity is to take the number of units. How many units we can take? But total value should be maximum after taking this number of units.
Okay, okay. So 20 plus 20 plus 10.
Mhm.
Okay.
Okay, so 240 we are getting. You cannot take any another combination, so you will to get more than this. So this is our greedy algorithm here. So this is called as a fractional knapsack problem. In dynamic programming, you will see 0, 1. So same type of problem, but you cannot take the partial value here. You have to take the complete item or you have to leave the item. So that condition, that is called 0, 1 fractional, 0, 1 knapsack problem. Okay, so that is actually solved by the dynamic programming. So this is solved by the greedy approach. So I hope this process is very easy. I hope you got the idea. So first step is just calculate the per unit item for per unit value for each item. After that, sort the items based on the per unit value in decreasing order. Then take the item from the highest per value. Okay. Then take how many units you can take. Okay. If that unit number of units is less than to the capacity, take all. Okay, and reduce your remaining capacity. Then take the second item. So repeat this process till when your capacity is finished, and then calculate the final. So you can try this. Okay. So I think idea is very clear, and this is simply calculation based problem or simple loop based problem. So just create the information of this and then apply the loop and condition. Okay. So I'm just leaving with the logic. You can just try this. And next problem, that is also very similar to your first problem. Again, the same things with the Hoffman tree. So this is also a same, write a function is code valid. Hoffman codes are given as a first parameter, message is also given. That accept a dictionary Hoffman code which in which key represents the characters and corresponding value represent the Hoffman code. Okay, and you are also getting a message, and then you need to check that message is valid or not. So what is the meaning of this? So here you have a Hoopman codes. Sorry. So A, you have the code like 000, B you have like 0010, C you have 0011, like all code you have. Now you are getting a message. So 101010 like this. Now you need to check this message is valid or not. So how you can check that this is also simple loop and checking based problem. So you can check, just traverse the digit and check if code is exist in this dictionary or not. So how you can do this? You can just reverse this dictionary. Just make the code first and value as a that key as a second. So after do you can do this like 000 as a. Okay, 0010 as a B, like okay, so 0011. Just make a reverse dictionary. After that, this is very simple. So for just take a strings like S and take first bit. This is one, and check this S is exist is this S is in D dictionary or not. So this operation can you can directly check. Okay, so key we can directly check. So S in dictionary or not. Okay, so this part will be matched with the dictionary. If not matched, just add one more bit in this. Okay, 0. Now, if this is a key or not, if not, then again add one more. Okay, like 1. Then this is a key or not? If not, then add more. So like, so once you will get any key match, so just uh, reset this as a empty. Okay, here we are just returning true or false. So in this process, once you get a key, just reset your S to empty. Again, start to the next. Okay, again add the next fresh bit. Okay, like 0. This is exit or not. So if you are getting this, and finally, and so this will match happen at the last actually. Okay, so after repeat checking for the all bits, if any bits are pending where there is no matched with the key, okay, that is not matched with any key of the dictionary, then that is not a valid actually message. Your message should be finished with all related character. So here like so here you can see we are getting true message, so that means this will create a message properly. So like this one, if you can see 1 1 is representing, so first two 1 is representing F. Okay, like 1 0 is representing E. So if you see E, then 1 1 again F, then 1 0 E, 0 1 is representing by D. Okay, 0 1 D, then 1 1 again F, then 0 0. This is no. So we have missed. Okay, 1 1 and
Yes.
then 1 0. Yeah. Huh. So we have missed one character. Otherwise, you will see this final thing in at the last bit actually. You will get all the match in the initially. At the last moment, if any bits are remaining and that is not matched in the key, at that time you can return to the false. If all are matched and you got all the matches, okay, and no digit is remaining, so then you will return true. Okay, so this is the logical step for this. First step is make this dictionary as a reverse dictionary. Just shift value as a key and key as a value. After that, this will become very easy process. Okay, by just taking the bit and check this is exist in the key or not. So in this way, you can try this and you can just validate. Okay, so these two problems are for you, and you can try by your own, and otherwise you can ask in the next session. Okay, so that's it for today, and if you have any query, then you can ask, otherwise you can close. Okay, so if there is no query, then we can close the session. Thank you everyone. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.